we present a discrete model of thin, flexible rods. Our model relies on the notion of parallel transport, which maps vectors along a smooth curve in a twist-free way. We define parallel transport along discrete curves analogously to the smooth case as rotations about the binormals at vertices, which transport vectors along the curve without twist. When a frame is parallel transported about a closed loop, the result is a rotation about the tangent vector. The angle of this rotation is known as the holonomy, an important concept also needed for our derivation. This animation illustrates how the shape of the curve affects parallel transport. The colors indicate the orientation of a frame prescribed at the left end and parallel transported over the entire curve. Observe how the frame at the right end turns as the torsion of the curve increases. This illustrates the link between the twisting of a rod and the resulting torsion on its centerline. Our discrete model can reproduce interesting phenomena, such as the formation of these structures known as plectonemes. The shape and behavior of these structures is highly sensitive to the physical parameters of the rod and the surrounding environment. Here, we show the behavior of elastic rods in experiment. This knot shows continuous and discontinuous changes in shape as the ends are twisted. Both of these are captured accurately using our discrete rod model. Twisting the knot in the opposite direction results in a very different shape, which is again reproduced faithfully by our model. When the cross-section of a rod is anisotropic, we observe a non-uniform distribution of twist over its length. This phenomenon is even more pronounced when the rod has a non-flat rest shape. Here we see a chain of rods with no prescribed material frame orientations anywhere along their length. Although we are not explicitly twisting the material frames anywhere, the material frames themselves are still required for modeling the undeformed curvature of each link in the chain. Here we can see an interesting experiment showing that when a helical rod is flattened out and the ends slowly brought back together, two helices of opposite chirality form in the middle. Using the same rest shape as the experiment, our model again reproduces this surprising result. We build on an efficient method for enforcing constraints in order to couple our system to rigid bodies. This plot shows the transfer of rotational energy from one rigid body to another via the twisting of the rod. This experiment, consisting of a rigid body attached to the end of a helicoidal rod, exhibits interesting interactions between the bending and twisting modes of a stretched spring. The motion of the rigid body varies from bobbing up and down to twisting side to side as the energy of the system is transferred back and forth between the translational and angular modes of oscillation. We can readily observe this complex interplay between the two modes in our simulation. Using our discrete model for elastic rods and coupling them through rigid bodies, we can connect rods in arbitrary ways to create complicated structures such as this tree. Thank you.